Hi guys, welcome to another lecture in the series General Inorganic Chemistry, and today we'll be continuing even further our conversation about chemical bonding. So the first area that we're going to mention is valence bond theory. And it really is a marriage of Lewis's notion of electron pair bonds and the idea of atomic orbitals that led to the model of chemical bonding called valence bond theory. And what it is really that bonding electron pairs are concentrated in the regions between the atoms, as we see in our diagram here. Our bonded pairs are concentrated in the regions between atoms, and the atoms that we see in that image is boron and fluorine. And so just to repeat, the bonding electron pairs are concentrated in regions between atoms, and non-bonding electron pairs lie in directed regions of space, as we saw previously. Now, by extending this approach to include ways in which the atomic orbitals can mix with one another, and later on we're going to discuss that image even further, we obtain an explanatory picture that corresponds to the VASPER model. So in Lewis theory, covalent bonding occurs when atoms share electrons because the sharing concentrates electron density between the nuclei, as we just saw, right? And so in valence bond theory, we actually visualize the buildup of electron density between two nuclei, as we saw, as occurring when a valence atomic orbital of one atom shares space and overlaps with a valence atomic orbital of another atom. All right, so don't worry if it's not very clear right now. I promise you it will get clearer. But just note here that in valence bond theory, we're saying that the electron density between the two nuclei occur when you actually have valence atomic orbital overlap, right? And that is basically what the valence bond theory is about. So this overlap that we're talking about allows for two electrons of opposite spin to share the space between the nuclei, forming a covalent bond. So these three examples to the right show how valence bond theory describes the coming together of two atoms to form a molecule. All right, so let's talk about this one. So we have hydrogen here, atomic hydrogen, and as you would have known, the electronic configuration for hydrogen is 1s, right? And so we're saying that we have two electrons, well, one electron in each 1s orbital here, and you would have known our s orbitals are spherical in shape, like a ball, right? So just imagine that you have that electron here and here in the orbitals, and then orbitals overlap to form covalent bonds. So it is the overlapping of the orbitals and the sharing of electrons that forms the molecule seen here, which is the hydrogen molecule, right? Which, as we know, is a diatomic gas. All right, so the second molecule that we're looking at here is HCl. And I'm sure it will be helpful if you write out the electronic configuration for chlorine, right? So let's just do that. All right, so there we have it, right? So that's 1s2, 2s2, 2p6, 3s2, and 3p5, right? So our valence electrons are here, right? All right, so as we can see there, the outermost electrons are in the 3p subshell, right? And so that is the orbital that literally overlaps with our 1s hydrogen orbital seen here, right? So as we know, our p orbitals are shaped like a dumbbell or 8, right? And so this represents our 3p orbital that is now overlapping with our 1s orbital for hydrogen. And so that is, how the valence bond theory accounts for this covalent bond seen here. And then we have the chlorine. Of course, you would know that chlorine is a diatomic gas as well. And so for that molecule, we can see where the covalent bond that is formed between the two chlorine atoms occur as a result of overlap of the two 3p orbitals, right? And essentially that is how the valence bond theory describes the coming together of two atoms to form a molecule. So in the example of the formation of hydrogen, each hydrogen atom has a single electron in a 1s orbital, as I said before. As the orbitals overlap, electron density is concentrated between the nuclei. So because the electrons in the overlap region are simultaneously attracted to both nuclei, which, that would make sense, they hold the atoms together, forming a covalent bond. So the idea of orbital overlap producing a covalent bond applies equally well to other molecules. And as we saw when I was explaining HCl, the chlorine, and we did write out the electronic configuration already, so this is just repetition. All the valence orbitals of the chlorine are full except one 3p orbital, which contains a single electron. So this 3p electron pairs with the single 1s electron of hydrogen to form the covalent bond that holds HCl together. So because the other two chlorine 3p orbitals are already filled with a pair of electrons, they do not participate in the bonding to hydrogen. So the same is true for chlorine gas. We can explain the covalent bond in Cl2 in terms of the overlap of the singly occupied 3p orbital of one chlorine atom with the singly occupied 3p orbital of another. Alright, so the valence bond theory therefore has helped us to account for or to describe the covalent bond in molecules. All right, so the next thing that we're going to talk about is hybrid orbitals. So the VSEPR model, simple as it is, we went through it some time ago, does a surprisingly good job at predicting molecular shape, as we saw, right? So despite the fact that it has no obvious relationship to the filling and shapes of atomic orbitals. So for example, we would like to understand how to account for the tetrahedral arrangement of the carbon-hydrogen bonds in methane in terms of the 2s and 2p orbitals of the central carbon atom, which are not directed towards the apices of a tetrahedron. So now we can reconcile the notion that covalent bonds are formed from the overlap of atomic orbitals with the molecular geometries that come from the VSEPR model. Or so that is indeed a question. How can we reconcile the notion that the covalent bonds are formed from overlap of atomic orbitals with the molecular geometries from that we saw with the VSEPR model? So to explain these molecular geometries, we often assume that the atomic orbitals on an atom, usually the central atom, mix to form new orbitals called hybrid orbitals, right? So at this stage, we're familiar with our S or spherically shaped S orbital or P orbital or D, F, etc. Right? So now we're saying that some mixing happens with regards to the bonding. So when atomic orbitals mix, they form new orbitals called hybrid orbitals. So as I was discussing some time ago, if you think about a hybrid orbit, if you think about anything that is a hybrid, it's usually a combination of two different things, and when they combine, they form something new, right? So think about your hybrid plants, two different plants coming together when to form a brand new plant. The same is true for atomic orbitals or hybrid orbitals. So the shape of any hybrid orbital is different from the shapes of the original atomic orbitals, right? Makes sense, right? Because if it's two different things mixing together, we get something new. So this process of mixing atomic orbitals is a mathematical operation called hybridization. Now, we're not going to go into the mathematical part of it. We're just going to literally just accept that when certain amounts of the orbitals mix together, this is the output. This is the new hybrid orbital. So the total number of atomic orbitals on an atom remains constant, right? So the number of hybrid orbitals on an atom equals the number of atomic orbitals that are mixed. Alright, so to help us to understand hybridization, we're going to use beryllium difluoride molecule as an example. So we see the Lewis structure here. We know that beryllium is number 3, hydrogen, helium, lithium, beryllium. So that's 4, right? And we know that fluorine is in group 7 of the periodic table. So based on the VSEPR model, it correctly predicts that beryllium difluoride is linear with 2 identical beryllium fluoride bonds, right? So the Lewis structure, we have gone through already how to draw the Lewis structure, right? So based on this Lewis structure, we have 2 electron domains, right? And based on the VSEPR model, if we have 2 electron domains, it means that that molecule is linear. We have 2 identical bonds there. So how can we use valence bond theory to describe the bonding? Well, we first look at the electronic configuration of fluorine. So that's 1s2, 2s2, 2p5. it indicates an unpaired electron in a 2p orbital. So much similar to our chlorine that we saw previously. So this electron can be paired with an unpaired beryllium electron to form a polar covalent bond. So the question is, which orbitals on the beryllium atom, however, overlap with those of the fluorine atoms to form these linear bonds that we refer to, right? And so to illustrate the process of, well, we said that already. So the idea here is that we want to know which orbitals overlapped, right, to form these two equal linear bonds. So first we have to look at the orbital diagram for ground state beryllium atom, and we see it here, right? So we have 4 electrons. So we have 1s2, 2s2 electronic configuration, ground state beryllium. So clearly we can see that it has no unpaired electrons, right? And so the beryllium atom in its ground state cannot bond with the fluorine atoms. There are no unpaired electrons. So the beryllium atom could form 2 bonds. However, by envisioning that we promote, or you might see the word excite, one of the 2s electron to a 2p orbital, right? So here we have one of the 2s electrons being promoted to a 2p orbital. So now we're going from two paired electron to one unpaired electron here. Or if we look at it like this, we know that there are different energy levels, right? So on excitation, one of the electrons is promoted to a higher energy level in a 2p orbital. So the beryllium atom now has 2 unpaired electrons and can therefore form 2 polar covalent bonds with fluorine atoms. The problem, though, is that those 2 bonds would not be identical. If you have the bond between that 2s electron and the other bond between that 2p electron, both of the bonds would not be identical. So let me just read what's here. The 2 bonds would not be identical. However, because a beryllium 2s orbital would be used to form one of the bonds, and a 2p orbital would be used to form the other, as I just said in different words. Therefore, although the promotion of an electron allows for 2 BeF or beryllium fluoride bonds to form, we still have not explained the structure, right? Because the structure has 2 equivalent or identical bonds. So this is how the hybrid orbitals come in, right? So we can solve this dilemma by mixing the 2s orbital with one of the 2p orbital to generate 2 new orbitals. So like p orbitals, each new orbital has 2 lobes. So we mix 1s and 1p atomic orbitals, and we get 2 sp hybrid orbitals. So as we said, like the p orbital, each new orbital has two lobes. So one lobe here, one lobe here. Unlike the p orbitals, however, one lobe is much larger than the other. So this lobe is much larger than this one. The two new orbitals are identical in shape, but their large lobes point in opposite directions, right? So these two new orbitals are hybrid orbitals because we have hybridized one s and one p orbital. We can call each hybrid an sp or a hybrid, sp hybrid orbital. So according to the valence bond model, a linear arrangement of electron domains implies that we have sp hybridization. So this is how we would know, right? The new orbital diagram for the formation of the two sp hybrid orbitals, right? So here we have our paired electron in the 1s subshell here, and we have the unpaired electrons in the sp. So we have two sp hybrid orbitals, one electron in each, and then we have two unhybridized p orbitals, right? So this is what literally happened. So there's a mixing of the 2s, well, the 2s orbital and one of the 2p orbitals, right? So these two mix up, right? And then that leaves the 2p, not 2p, but 2p. So orbitals here that are unhybridized. So that's what we're seeing here, the two unhybridized p orbital, and we're seeing the two hybrid orbitals. So the electrons in the sp hybrid orbitals can form bonds with the two fluorine atoms now. So because the sp hybrid orbitals are equivalent but point in opposite direction, the beryllium difluoride has two identical bonds and a linear geometry. So we have used one of the 2p orbitals in making the hybrids. The remaining two 2p atomic orbitals of beryllium remain unhybridized and are vacant, as we see up here, right? So this is our sp, or two sp hybrid orbitals here, overlapping with our 2p orbital for fluorine. So we have two overlaps, and here, this diagram, we have our sp orbital here, and then we have the two p orbitals, so the unhybridized p orbital here, and the second unhybridized p orbital. So one is vertical, the other is horizontal in the same plane as the sp orbital, right? So this is literally how it looks. So that is the sp orbital. So now we're going to look at the sp2 and sp3 hybrid orbitals. So whenever we mix a certain number of atomic orbitals, we get the same number of hybrid orbitals, as we have said a number of times. Each hybrid orbital is equivalent to the others but points in a different direction. Thus, mixing one 2s and one 2p atomic orbital yields two equivalent sp hybrid orbitals that point in opposite directions, as we saw. other combinations of atomic orbitals can be hybridized to obtain different geometries, right? So in boron trifluoride, for example, mixing the 2s and 2 of the 2p atomic orbital yields 3 equivalent sp2 hybrid orbitals. So here we have the electronic configuration of boron, which is 1s2, 2s2, 2p1, right? So here we have one paired, so this is paired electrons, and we have one electron that is unpaired. So this paired electron cannot participate in a covalent bond. It has to become unpaired, right? And then we can have the overlapping. So what happened in this case is that we have this 2s subshell and 2 of the 2p orbitals mixing together, and clearly that leaves one of the 2p orbitals unhybridized. So 1, 2, 3 mix together to form 3 sp2 hybrid orbitals. Right? So we have one s orbital mixing with 2 p orbitals to form 3 sp2 hybrid orbitals seen here. And so in a similar fashion as we did or we saw for beryllium, right? We see here, and we're not seeing the 1s2 electron. We're seeing the 2s electron, the paired electron, and the 2p electron. And upon promotion or excitation, so this is the ground state configuration of boron. And so upon excitation, we have one of these electrons being promoted to from 2s subshell to a 2p subshell seen here, right? And then after that, you have hybridization. So these 3 subshells mix or become hybridized, right, to form 3 sp2 hybrid orbitals that are clearly equal in energy. Because notice here that we have E represents energy here, so it's low energy, high energy. So we have 3 sp2 hybrid orbitals, and then we also have one 2p subshell that is still unhybridized and vacant here. So the 3 sp2 hybrid orbitals lie in the same plane, right? So this is how it looks in the same plane. So just imagine it being on a sheet of paper, right? 120 degrees apart from one another. So that's the angle between here, 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 and here, and here, and here. So it's like a triangle pretty much. So they are used to make 3 equivalent bonds with the 3 fluorine atoms, leading to the trigonal planar molecular geometry of BF3. So notice that an unfilled 2p atomic orbital remains unhybridized. So this is here, that this is a p orbital that remains unhybridized. It's oriented perpendicular to the plane defined by the 3 sp2 hybrid orbitals, with one lobe above and one below the plane, right? So above and below the plane. So an s atomic orbital can actually mix with all three p atomic orbitals in the same subshell, right? So here we're talking about sp3. We were just talking about sp2, and now we're talking about sp3, where you have one s atomic orbital mixing with all three of the atomic orbitals. So with sp, it was just one p orbital that was mixed. In sp2, it was two p orbitals that were mixed. And with sp3, you guessed it, three p atomic orbitals were mixed in the same subshell. So, for example, the carbon atom of methane forms 4 equivalent bonds with the 4 hydrogen atoms. So we envision this process as resulting from the mixing of the 2s and all three 2p atomic orbitals of carbon to create 4 equivalent sp3 hybrid orbitals. All right, so let's look at it here. We know the electronic configuration of carbon already, right? So we know that we have 2 electrons in the 2s2 subshell, and we have 2 electrons in the 2p2 2p subshell. So 2 electrons in the 2s, 2 in the 2p. So as it is now, this pair is paired, right? So for that covalent bond to form, we want this pair to be unpaired, which requires therefore that it is no longer in the ground state, but it becomes excited and promotion happens. Well, one of these electrons become promoted or excited to the vacant 2p subshell, right? So this is the excited state of carbon when we have promotion of one of these electrons to a vacant 2p subshell here. After that, you have the hybridization that we've been talking about, which is the mixing. So 1s and 3 p orbitals mix up and we form 1, 2, 3, 4 hybrid orbital, because as we said, if we mix 1, 2, 3, 4 orbitals, we will get the same amount of hybrid orbitals. So here we can see that we got 4 sp3 hybrid orbitals. So each sp3 hybrid orbital has a large lobe that points toward one vertex of a tetrahedron. Now, these hybrid orbitals can be used to form 2 electron bonds by overlap with atomic orbitals of another atom, such as hydrogen in methane, right? So using this valence bond theory, we can describe the bonding in methane as the overlap of 4 equivalent sp3 hybrid orbitals on carbon, which is our central atom, with the 1s orbitals of the 4 hydrogen atoms to form 4 equivalent bonds. So this is basically what it looks like. So it looks like a tetrahedral, right? So 4 sp3 hybrid orbitals form a tetrahedron. And if we add our hydrogens, right, they combine, the sp3 and the 1s. So it's the overlap of the 1s and the sp3 that, according to the valence bond theory, produces the 4 equivalent covalent bonds. So in a similar fashion, we can see here that we have one s and or three p orbitals, right? And they all mix together to form four sp3 orbitals. And as we know, it's shaped like a tetrahedral, and therefore the angle is 109.5 degrees. So here we see that, for the atomic orbital set sp, when we mix one s and one p, we end up with two sp hybrid orbital set, and that geometry is linear, and therefore the angle is 180 degrees. And we see some examples of compounds that fall in this category. In the second row, when we mix one s and two p orbitals, we end up with three sp2 orbitals, which has a geometry of trigonal planar. And so, we have 120-degree angle between these two lobes here. And these are some examples of some compounds which fall in that category. And then finally, when we mix an one s and three p orbitals, we get four sp3 orbitals. So 1, 2, 3, 4. And of course, the geometry is tetrahedral, and the angle here is 109.5. So we have a number of compounds here that fall in that category. So what are the steps, right? For the hybrid orbital description of bonding in ammonia. So firstly, what we want to do is to draw the Lewis structure of ammonia, right? And then so let's read here. The following steps allows us to describe the hybrid orbital used by an atom in bonding. So firstly, draw the Lewis structure of the molecule or ion. So we have the Lewis structure here. Second step, use the VSEPR model to determine the electron domain geometry around the central atom. So clearly we can see here that we have 1, 2, 3, 4 electron domains, and because of that, the geometry, the electron domain geometry would be tetrahedral. So the third step is specify the hybrid orbitals needed to accommodate the electron pairs based on their geometric arrangement. So based on that, we have an sp3 hybridization occurring for ammonia. All right, that leads us to a question which says, describe the orbital hybridization around the central atom in NH2 minus, right? So what you want to do here is to pause the video and try to answer the question. So firstly, you draw your Lewis structure. The second one, count your electron domains. And then the third one is this, to specify the hybrid orbitals needed to accommodate the electron pairs. So if this is what you got, if you got tetrahedral, then and therefore sp3, then you would have gotten it correct, right? So we have 1, 2, 3, 4 electron domains. And therefore the electron domain geometry is tetrahedral, and that would correlate to the sp3 hybridization. All right, so the next thing that we're going to look at, or the final thing that we're going to look at for this lecture, is molecular orbitals, right? So while the valence bond theory helps explain some of the relationships among Lewis structures, atomic orbitals and molecular geometries, it does not explain all of the aspects of bonding. It is not successful, for example, in describing the excited state of molecule, which we must understand as we saw to explain how molecules absorb light, giving them color. So some aspects of bonding are better explained by a more sophisticated model called the molecular orbital theory, or you might see MO going forward. So in a similar way, molecular orbital theory describes the electrons in molecules by using specific wave functions. We're not going to go into these wave functions, but it's important to mention it, each of which is called a molecular orbital. So molecular orbitals, they have many of the same characteristics of atomic orbitals, and these are some of the similarities. One, a molecular orbital can hold a maximum of 2 electrons with opposite spins, right? So that is true for atomic orbitals as well. The second similarity is that it has a definite energy, right? There's a definite energy associated with the molecular orbitals. But unlike atomic orbitals, so this is the difference or differences. However, molecular orbitals are associated with an entire molecule, not with a single atom, right? So that is the difference. It's associated with an entire molecule and not with a single atom. All right, so we will use the 2s atomic orbital because, that's the simplest. So molecular orbitals of hydrogen molecule, it's the simplest molecule, and that we can use as an example to explain molecular orbitals. So we're going to use it to construct molecular orbitals for hydrogen, right? So this is our example. Whenever 2 atomic orbitals overlap, 2 molecular orbitals form, right? Thus, the overlap of the 1s orbitals of 2 hydrogen atoms to form a hydrogen H2 produces 2 molecular orbitals. So here we have 1s. So this is the 2 hydrogen atoms by themselves, and when you have constructive combination, it leads to the bonding hydrogen molecular orbitals. And when you have the upper one here, when you have destructive combination, it leads to anti-bonding hydrogen molecular orbitals. So the first molecular orbital, which is shown at the bottom right, that's here, is formed by adding the wave functions for the 2 1s orbitals. We refer to this as I said before, as constructive combination. And so the energy of the resulting molecular orbital is actually lower, because notice here we have our energy scale here. So this is the energy of the atomic orbitals, and the molecular orbital is actually below it. So therefore, the energy is lower in than the 2 atomic orbitals from which it was made, and it is called the bonding molecular orbital. So the second molecular orbital is formed by what is called destructive combination, combining the 2 atomic orbitals in a way that causes the electron density to be cancelled in the central region where the 2 overlap. So the energy of the resulting molecular orbital, referred to as the anti-bonding molecular orbital, so that's these nodal plane between the nuclei, Uh, so the energy of the resulting molecular orbital, referred to as the antibonding molecular orbital, as I said, is higher than the energy of the atomic orbitals. And so the antibonding molecular orbitals of hydrogen is shown at the top right. So that's up here, right? So higher in energy. So this is our atomic orbital. So our antibonding molecular orbitals are actually higher in energy. So the electron density in both the bonding molecular orbital and the antibonding molecular orbital of hydrogen is centered about the internuclear axis, right? So the electron density concentrated between the nuclei, so in the middle here. Molecular orbitals of this type are called sigma molecular orbital, and that is the sigma symbol for sigma here. By analogy for sigma bonds, the bonding sigma molecular orbitals of hydrogen is labeled sigma 1s. So 1s, that is the orbital, and sigma is the representative or symbol for the molecular orbital. The subscript indicates that the molecular orbitals is formed from two 1s orbitals. As I said, the antibonding sigma molecular orbital, which is here, right, is labeled as sigma star 1s. So the asterisk denotes that the molecular orbital is anti-bonding. So the relative energies of the two 1s atomic orbitals and the molecular orbitals formed from them are represented by an energy level diagram, also called the molecular orbital diagram, seen here to the right. Such diagrams show the interacting atomic orbitals on the left and right, and the molecular orbitals in the middle. All right, so we have hydrogen atom, that's to the left and to the right, and we have the molecular orbitals in the middle, right? So this is in the middle. So like atomic orbitals, each molecular orbital can accommodate two electrons with their spins paired, which is representative or synonymous with our Pauli exclusion principle. Right? So this is our energy level diagram, also called a molecular orbital diagram. And it has, the hydrogen atoms here because we are forming diatomic gas. So what we're seeing here is that we have one electron in our 1s orbital, one in our 1s, and for the bonding molecular orbital we have one electron from here, the other from here, and we have a vacant anti-bonding molecular orbital. All right, so another term that we need to know is bond order, right? So bond order is equal to half the number of bonding electrons minus the number of antibonding electrons. So what you want to do here, once you have, accounted for all of your electrons, so if we have 2 electrons here, both electrons will go in our bonding molecular orbital, right? And so here we don't have any antibonding electrons. So in molecular orbital theory, the stability of a covalent bond is actually related to its bond order, defined as, we already defined it, half the difference between the number of bonding electrons and the number of antibonding electrons. We take half the difference because we are used to thinking of bonds as pairs of electrons. So a bond order of 1 represents a single bond, a bond order of 2 represents a double bond, a bond order of 3 represents a triple bond. So because molecular orbital theory also treats molecules containing an odd number of electrons, bond orders of half, 1.5, etc. are actually possible. So calculate the bond order of hydrogen, right? So that's quite simple. All we have to do is to say how many electrons are in the bonding molecular orbital. So here we count 2. How many are in the anti-bonding molecular orbital? It's 0, right? So half of 2 minus 0 is what? Is 1. So remember, when we get a bond order of 1, it means that we have a single bond. All right, so let's try another molecule. Period 2 diatomic molecules. So the following rules summarize some of the guiding principles for the formation of molecular orbitals and for how they are populated by electrons. So the first step, the number of molecular orbitals formed equals the number of atomic orbitals combined. So for hydrogen, we have 2 atomic orbitals, so we formed 2 molecular orbitals, right? So that is consistent there. Atomic orbitals combined almost effectively than other atomic orbitals of similar energy, right? So here we have a 1s orbital combining with a 1s orbital, similar energy. All right, we're good so far. The third one is the effectiveness with which 2 atomic orbitals combine is proportional to their overlap. That is, as the overlap increases, the energy of the bonding molecular orbital is lowered and the energy of the antibonding molecular orbital is raised. And then fourthly, each molecular orbital can accommodate at most 2 electrons with their spins paired, right? So here we have our orbital with 2 electrons and spin paired. And the fifth guiding principle is when molecular orbitals of the same energy are populated, 1 electron enters each orbital with the same spin before spin pairing occurs, right? So if you haven't, or if you don't remember, you can look back at Hund's rule. All right, so let's see if we can use that to put together another molecular orbital, this time using lithium. So lithium has an electron configuration of 1s2, 2s2, right? Sorry, not 1s2, 1s2, 2s1. So 3 electrons. So when lithium metal is heated above its boiling point, which is very high, 1342 degrees Celsius, lithium molecules are found in the vapor. Li2 molecules are found in the vapor phase. And so the Lewis structure for Li2 or lithium indicates a lithium-lithium single bond, right? So let's look at our guidelines again. The first one is that the number of molecular orbitals formed equals the number of atomic orbitals combined. So here we count 1, 2, 3, 4 atomic orbitals, and we have 1, 2, 3, 4 molecular orbitals. So the second rule is that atomic orbitals combine most effectively with other atomic orbitals of similar energy, right? So here we see that the 1s combines with the 1s, and the 2s combines with the 2s because they are of similar energy. All right, so let's skip to 4. Each molecular orbital can accommodate at most 2 electrons with their spins paired. And then 5, when molecular orbitals of the same energy are populated, 1 electron enters each orbital before spin pairing occurs. All right, so here, let's go back to this. All right, so let's check to see if we have 2 electrons with their spin paired, right? So here we have a total of 4 electrons. 2 in here, 2 and 2 gives us 4. So we have 2 electrons going here in the bonding molecular orbitals, and an orbital, and then we have 2 electrons going in the non-bonding molecular orbital, right? And here we have 1 electron, similar to what we saw with hydrogen, but they're in the 2s orbital, and when they combine, they go into the bonding molecular orbital. So there is no electron here in the non-bonding molecular orbital. All right, so here, we have our sigma 1s or sigma star 1s, and I think I said non-bonding, it should be anti-bonding. So we have 2 anti-bonding molecular orbitals, and we have 2 bonding molecular orbitals, sigma 1s, sigma star 1s, sigma 2s, and sigma star 2s. So this is vacant, and this will be sigma 2s. So 2 electrons here, and 2 here, and 2 here. So this is our molecular orbital energy level diagram for lithium Li2. All right, so that's all for now. See you guys next time.